All right, so this week we're on lecture five. I think most of you have already uploaded homework one, two, three, and four, and most of those have already been graded. Um, so I'm going to, yeah, let me make sure that I have the transcript running. Good. So today we'll start with lecture five. I'm going to go ahead and start the Jupyter Notebook in the usual way. I'm actually going to open a terminal and just type Jupyter Notebook. And then we'll navigate to the course directory and go to lecture five. We've finished now with all of the core data structures and all the core syntax of Python. You've now learned about lists and you've learned about tuples and you've learned about dictionaries. Lists and tuples are quite similar, right? They're each linear sequences of objects. You can put any sequence of objects into a list. You can put any sequence of objects into a tuple. The only difference between them really is that the tuple can't be changed after you've created it and the list can be changed after you've created it. The dictionary, on the other hand, can take any object as an index and look up any other object. So that's all you need to know from the core of Python. This week we're going to learn about NumPy and Matplotlib. NumPy is the package in Python that's used for numerical calculations. So the NumPy array is very similar to a list, but it's much more computationally efficient. One of the things that we give up in order to make it more computationally efficient is the flexibility in data types. In a NumPy array, all of the elements of the array have to be the same data type. So they need to all be, normally they need to all be integers or they need to all be floating point numbers. Very rarely will we use NumPy arrays to store strings. It's possible, but it's not very convenient. Matplotlib is the plotting package in Python. It's actually called Matplotlib because it's modeled after a commercial numerical computation package called MATLAB, and it's basically designed to be as easy to use for plotting as possible. And Matplotlib works with numerical arrays in order to plot them in a variety of ways that are useful for scientific computation. So before we start working on speech and audio, which will begin next week, this week, first we need to learn about numerical calculation and plotting. NumPy is the package for numerical calculation, and this is descriptions of the NumPy release. So this is the fundamental package for scientific computing with Python, and that really is correct. All of the other scientific computing packages in Python are based on NumPy. So everything that's used to train artificial intelligence, everything that's used to do scientific computing is built on top of NumPy, which is the basic numerical calculation package. So let's start out by looking at linear algebra. When you take, I mean, you can see that we have square brackets here, x1, x2, and x3. When you take these three numbers, 0.1, -4, and 0.25, and stack them up into a list, you can think of that list as a vector. A vector is just a list of numbers, right? And you can, if it's in 2 dimensions, you can think of it as x and y coordinates. If it's in 3 dimensions, you can think of it as x and y and z coordinates. I'm going to use the letter x to denote the entire vector, and I will use the symbol x1, x2, and x3 to denote the elements of that vector. Similarly, I'll use the letter y to denote another entire vector, and the symbols y1, y2, and y3 will denote the elements of that vector. So first of all, we'll import NumPy. This is a separate package that can be imported just the same way that we always import our homework. NumPy is distributed with Anaconda. So if you used Anaconda to install Python on your computer, normally NumPy is already distributed. So if you import NumPy and get no errors, then that worked. However, using the whole word numpy to specify the objects that you want, for example, numpy.array, becomes kind of time consuming. So normally we define an abbreviation. We import numpy as np. And that creates an abbreviation for the name numpy. So that then if we want to create a numpy array, we can create a numpy array by taking the list 1, 2, 3, 4, 5 and turning it into a numpy array. So if I execute this code, you'll see that y here is the list 1, 2, 3, 4, 5, and x is the numpy array that's been created from that list. So I've just taken a list of numbers, 1, 2, 3, 4, 5, and I've converted them into a numpy array. NumPy arrays have some additional properties. We can say, we can find out, for example, what the type of numbers are. I think that's called x.dtype. Let me find out. Yeah, its numbers are of type integer 64. So in this case, all of the numbers in that array are integers. But if I change just one of them to a floating point number, let's say I change the second one to from 2 to 2.1, then the NumPy array will automatically be created with floating point numbers. Now 1 has been converted to 1.0. 3, 4, and 5 have each been converted to 3.0, 4.0, and 5.0. They're all floating point. And furthermore, they're a 64-bit floating point. NumPy by default stores every floating point number with a 64-bit number. Let's see, I think even the integers were already 32 bits. No, even the integers are already 64 bits, which is twice the normal bit width of numbers in Python. In Python, normally the floating point, all of the numbers would be 32 bits, but in NumPy, there are 64 bits. That's because when you're doing scientific calculations and artificial intelligence calculations, you often want more precision than you would if you were doing simple arithmetic. The main reason that we use NumPy is because we can treat it as a linear algebra package. Linear algebra is the branch of algebra that deals with vectors and matrices. So for example, x transpose y means we compute the dot product between this vector x and this vector y. So if I define x to be the NumPy array that has 0.1, -4, and 0.25, and if I can define y to be the NumPy array that has 3 and 0.2 and 5, then the dot product between these two vectors, x transpose y, is just the sum from I equals 1 to 3 of x sub I times y sub I. So it's 0.3 minus 0.8 plus 1.25. So let's see, it's 0.1 times 3, which is 0.3, minus 4 times 0.2, that's minus 0.8, plus 0.25 times 5, which is plus 1.25. So when I take the dot product of those two numbers, I get the result 0.75. And this is maybe the most critical concept in all of machine learning and artificial intelligence, is that we can take two long lists of numbers, each of which specifies the meaning of a word or a location in space or the position of a robot or the spectrum of a speech signal. There are so many different things that can be represented as lists of numbers. We can take that list of numbers and convert it into a NumPy array, right? We take that list and convert it into a NumPy array, and then we can take its dot product with another list of numbers. And that dot product tells us something about the similarity between this list and this list. For example, 0.75 is rather small, but if I were to convert this -4 to a +4, then all of the elements of this list and all of the elements of this list have the same sign. And by converting the -4 to a +4, I've made these two vectors more similar because all of their elements have the same sign. And so their dot product becomes larger, 2.35. If I make them more different, if I make their signs all kinds of different directions like this, then the size will be smaller, -1.75. In fact, it looks like the most dissimilar that I can make these two by just changing their signs is to change it to -4, in which case the dot product is 0.75. That makes these two vectors as dissimilar as possible. The other thing that linear algebra concerns itself with is matrices. So we can take the dot product we can take a vector multiplied by a matrix. If the vector is a column vector, we can take X transpose and multiply it by the matrix W. And what that means is we create a new vector, V, whose first element is the sum of x1 times w11 plus x2 times w21 plus x3 times w31. All of those go in the first element of the vector V. And that gives us minus 3.65. The second element times w12 plus x2 times w22 plus x3 times w32. And if the middle column of w are all zeros, then that vector x multiplied by all zeros gives us 0 at the output. And so on. If the last column are all minus ones, then the last element is the opposite, obviously, 3.65. So if I create w as a list, I'll create a list of lists, right? Each list here is one row of the matrix W. So 1, 0, minus 1 is the first row. And 1, 0, minus 1 is the second row. And here 1, 0, minus 1 is the third row. I'll create that list and then I'll turn it into a NumPy array. If I take a list of lists and turn it into a NumPy array, then it's automatically interpreted as a matrix, as shown here. 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1 is of type class numpy.nd array. And then if I want to multiply the vector x times the matrix W, then I can use the numpy matrix multiply command. np.matmul means take the multiplication of this vector times this matrix, and the output then is the vector shown here. I can also multiply two matrices together. Let's see what happens if we multiply the matrix W times the matrix W. Oh, if we do that, we get a matrix that's all zeros. Let's see what happens if we multiply W transpose times W. If we do that, we get the matrix 3, 0, minus 3, 0, 0, 0, minus 3, 0, 3, and so on. So this is W transpose multiplied by W. This is W multiplied by W. This is V multiplied by W. Oops. I want X multiplied by W. Vectors will be automatically transposed. We're actually multiplying X transpose times W, but the result is the same because vectors will be automatically transposed by NumPy as necessary in order to make the multiplication work. I'll get very different results, though, if I multiply X transpose times W versus X transpose times W transpose times W. Let's see. I think I need two separate matrix multiply commands for this. Let's try this. If I multiply W times W, I get zeros, but if I multiply W transpose times W, I get something else. Anyway, these commands numpy dot dot, np dot dot, and np dot matmul are the key commands for linear algebra. Anytime that you want to do computations of long lists of numbers, the dot product and the matrix multiply are the operations that you really want. Because they're so useful, there is a shorthand that you can use, and that's just the at symbol. The at symbol between two vectors means take the dot product. The at symbol between a vector and a matrix means take the matrix multiply. So if I just take x at y, that means take the dot product of vector x and vector y. If I take x at w, that means compute the matrix multiplication of the vector x times the matrix w. And you see the results. So we can do any linear algebra. It's worthwhile to use pencil and paper to write out what it is that you plan to do. Here I've used Markdown. I've used the Jupyter Notebook to write out what I'm trying to accomplish. Because sometimes this notation, the matrix multiply notation in Python, can become a little bit difficult to understand. So here, for example, I'm going to multiply X transpose times W transpose, and I'll get something very different from what I would get if I multiplied X transpose times W. But if I multiply x times w, I will get the same thing because NumPy automatically computes the transpose. So that kind of thinking is easier if you write it out with pencil and paper so that you can understand what it is that you're trying to compute. All right, so that's really the main reason that we're going to use NumPy is for linear algebra. The main functions that we're going to use in NumPy are NumPy dot to take the dot product of two vectors and NumPy matrix multiply, NumPy matmul, to take the multiplication of a vector with a matrix or of two matrices, one with the other. Those are the key operations from which a neural network is created. NumPy has these additional operations, though, that are array mathematics. So, for example, if x is 0, 1, 2, 3, then x squared in NumPy means that you take every single element of x and square it individually, right? That's different from taking x dot product x, right? So if I take, let's just say x squared is that, we can take x times x array math is, and let me print out what that is, x times x, and then let me print x dot product x, linear algebra is, and let me print out x dot product x. And you'll be able to see that the linear algebra product, the at sign, is very different from the array algebra, which is the star sign. And then let me print a space after that. And then I'll print pi. And numpy.pi is the constant, 3.14159, etc. And if we take x and multiply it by pi, then that will create the array 0, 3.14159, 6.28, etc. And then we can take the cosine of that. Numpy.cosine is an array arithmetic that computes the cosine of every element of the x vector one at a time. So we get x is 0, 1, 2, 3, x squared is 0, 1, 4, 9. That's this operation where we've taken the array x and squared every element. X times x is 0, 1, 4, 9 also. That's where we've used the star symbol to multiply every element of x with the corresponding element of x. However, if we take the dot product using the at symbol, we get something very different. We get 0 times 0 plus 1 times 1 plus 4 times 4 plus 9 times 9, which totals 14. That does, oh no, we get 0 times 0 plus 1 times 1 plus 2 times 2 plus 3 times 3. That gives us 14. So that's 9 plus 4 plus 1. Then finally, pi is 3.14159, etc., etc. X times pi is 0, and then pi, and then 2 pi, and then 3 pi. And if we take the cosine of each of those, the cosine of 0 is 1, the cosine of pi is minus 1, the cosine of 2 pi is 1, and the cosine of 3 pi is minus 1. So you can see we get each of those elements. Let's try actually taking x times pi over 2. Let's try taking numpy times pi, numpy pi times x over 2, and we'll get slightly more interesting numbers. We have 0, and then 1/2 of pi, and then pi, and then 3/2 of pi. And the cosine of that, the cosines are 1, and then 0, essentially, right? 6 times 10 to the minus 17 is 0, and then minus 1, and then 0. Negative 1 times 10 to the minus 16 is basically 0. So in this way, we can create different numbers. We can multiply pi times every element of x and then multiply it by 1/2. We can take the cosine of the result. If you want to know whether any given operation in NumPy works on the vector, works on the linear algebra, or works on the array, you have to look it up. And you can easily do this by just searching. You can type numpy matmul, and it will bring you to the appropriate table. Numpy.matmul. Here's the information about that function. Or you can print numpy cosine, and it will take you to the numpy cosine information. Maybe switch to a stable version. Here's numpy.cosine. Notice that it lists here numpy.cos. We've been calling it np.cos. That's because I defined np to be an abbreviation for numpy. Way back up here at the beginning, I said import numpy abbreviated as np. And that's the way we'll usually use it. All right, the only other thing that you need to know about NumPy today is that there are a number of special arrays that you can create. So you can create an array that contains all zeros. In this case, I'm going to create an array which is two planes. Each plane has 3 rows, and each row has 3 columns. Here I'm going to create an array of all ones. This will be a 3 by 3 matrix of all ones. Here I'm going to create an identity matrix. It's spelled EYE, which in English is pronounced I. I is an abbreviation for the word identity in English, which is this matrix. It's the matrix that has a 1 in every element on the main diagonal and a 0 in all of the other elements. We can also create a range. The arange function is the integer range from 2 until just before 6. So this will be the range 2, 3, 4, 5. We can also create an array which is linearly spaced between 0 and 1 with six points on that range. So let's multiply these out and see them. Here's first of all the zeros array. It has 2 matrices, and each matrix is a 3 by 3 matrix of zeros. Right? So it has 2 separate matrices. Each matrix is a 3 by 3 matrix of zeros. O is a 3 by 3 matrix of ones. I is a 3 by 3 identity matrix. It has ones on the main diagonal and zeros everywhere else. R is the range that goes from 2 to just before 6. Let's make R go from 2 to just before 16. That will be interesting. So now it goes 2, 3, 4, 5, 6, all the way up to 15. And just like with the range function in regular Python, we can add a spacer here to say I want to calculate the elements that are from 2 to just before 16 spaced out by 2. And that will give me the numbers 2, 4, 6, 8, 10, 12, and 14. The linear spacing here finds 6 elements going from 0 through 1 inclusive. Notice that the A range ends before it gets to 16, right? It ended at 14. Linear space by default doesn't. Linear space by default, it includes the last element. And if we search for it, we'll find that that's an option. So if you look up the linspace function, you can see that it has the start and the stop and the number of steps. And then you can specify whether you want it to include the endpoint or not. This fourth optional argument can be used to specify that you don't want the endpoint. So if we go back here, we've created a range that has 6 steps between 0 and 1, including 0 and 1. And with the other four steps are 0.2, 0.4, 0.6, and 0.8. But if I wanted to have 6 steps not including the endpoint, then I could specify endpoint equals false. And in that case, I get 6 steps ranging between 0 and 1, but not including 1. It ends with 5/6. So this is 1/6, 2/6, 3/6, 4/6, and 5/6. Right? And I got that by specifying endpoint equals false. So it depends on, you can use that endpoint parameter to specify exactly what kind of array you want. All right, those are the key things that you need to know about NumPy. You need to know linear algebra. You need to know, that is, matrices and vectors. You need to know array mathematics. Those are functions like cosine and square and the array multiply that are applied to each element of the array separately. Then you need to know these special arrays: zeros, ones, the identity matrix, the range matrix, and the linear spacing. The other thing that, so you need to know those vectors because those are the fundamentals of all of machine learning. That's what machine learning is built on. Those are also useful to know if you want to create pretty plots. Matplotlib is used to create plots. The things that you can do in Matplotlib are just amazing. Um, so we can do, yeah, here are some examples of different plots that can create in Matplotlib. We can do things like you would do in Excel, bar plots and scatter plots and stem plots and stairs. We can also do statistical distributions, histograms, pie charts, violin plots, box plots. We can do images, color mesh and image show. We can do stream plots. Look at all the little vectors on there showing where the streamlines are going in this fluid flow simulation. Contour plots. You can do completely irregularly gridded data. You can do three-dimensional plots. And then all of those can also be done in multiple colors. Here they're being shown all in blue on white, but if you want to do them in multiple colors, you can also do that. So the Matplotlib, this gallery shows examples, and the tutorial page shows how to create those all of those different examples. So you can click through to any of these. If we want to do this example, here's all of the code to create this example with smiley faces. It's a tremendously powerful tool with a lot of different options that are worth learning about. All right, I'm running out of space here, so let me get rid of some things. All right, so for today, let's just learn the basics. Let's learn how to plot things, and let's learn how to create a stem plot. So first of all, we need to import Matplotlib just to make sure that it works. Uh, have I? It looks like I've somehow frozen my screen, so I'm going to quit and then restart. Let me restart Jupyter Notebook. And then I'll go ahead and go to the same page again, lecture 5, notebook.ipynb. And let's just run everything until we get down to Matplotlib. Here we go. So the other useful module we're learning about is Matplotlib. First of all, test to make sure that you have it installed. Just do import Matplotlib. And if that works, that means that you've got it installed. Just like with NumPy, it gets kind of tiring to write out Matplotlib every time. In fact, there are different subsections within Matplotlib. The standard plotting package is called matplotlib.pyplot. And so if we import matplotlib.pyplot as PLT, then from then on, we can start all of our functions with PLT rather than with matplotlib.pyplot. So for example, the way that there are many different ways to use it, actually many different ways to use it. The way that I like to use it usually is to create a figure using the plot.figure, and then to take that object, the figure object f, and to create subplots in that figure. So f.subplots here is creating a 2x2 grid of subplots, as shown here. And that 2x2 grid then will be the indexed in S. So S will have subplot 0, 0, subplot 0, 1, subplot 1, 0, and subplot 1, 1. So this is the way that I like to do it. One reason I like to do this is this allows me to specify the size of the figure. So 14 means it's 14 centimeters wide, and 4 means that it's 4 centimeters tall. Roughly speaking, those are centimeters on my display. I'm not sure how they appear on your display. This layout equals tight. This optimizer says that I want to have just exactly the right amount of room for all of the plot titles and all of the axis labels. So what layout equals tight means is that before it shows it to me, it will rearrange the plots so that everything fits. Here I'm printing out f as an object of type of. So when I print that, it says f is an object of type class matplotlib.figure.capital F figure. That's the class of the object. And this particular object now has The first plot, plot 0, 0, has the numbers 1, 1, 1, and 1 plotted as a function of 1, 2, 3, 4, 5. So on the x-axis, we have 1, 2, 3, 4, 5. On the y-axis, they're all ones, 1, 1, 1, 1. If I want to see each individual point, I can just specify a marker here. So now we'll see the markers, 1, 1, 1, and 1. If I want to specify that with a particular color, then I can specify the color. For example, G means green, green circles, or maybe I can specify green X's. These will be specified by default with the English terms. So yellow, Y for yellow, or R for red. Creates little red stars. All right. The O's are probably the most useful. So let's go back to using O's. All right. The second plot, plot number 0, 1, I'm plotting here 1, 2, 3, 4, 5 are the x-axis, and the y-axis are 1, minus 1, 1, minus 1, 1. And so you can see 1, minus 1, 1, minus 1, 1. So this is plot 0, comma 1. In plot 1, comma 0, I'm plotting 1, 2, 3, 4, 5, and on the y-axis, 1, 2, 3, 4, 5. So you can see the x-axis is 1, 2, 3, 4, 5. The y-axis is 1, 2, 3, 4, 5. Let's make that a little bit clearer by plotting that also using circles. So now you can see there are 5 dots here, 1, 2, 3, 4, 5. I think I can specify like this to get both circles and lines. Let's find out. Yeah, that worked. So I got circles with a line connecting between them. And then finally, in the last plot, I've got 1, 2, 3, 4, and 5 on the x-axis, and minus 1, minus 2, minus 3, minus 4, and minus 5 on the y-axis. Let me plot those also with circles with a line connecting them. So we can see those points are minus 1, minus 2, minus 3, minus 4, and minus 5. That's the basic plotting mechanism. In case you haven't noticed, I've been specifying the arguments as lists, right? This is a list of numbers, 1, 2, 3, 4, 5. But it's far more useful to specify them as NumPy arrays, because then you can do calculations like dot product and matrix multiply and sine and cosine and plot the results. So here, for example, I'm going to create a figure, which will be again size 14 centimeters by 4 centimeters. And I'll just create a single subplot. And since it's a single subplot, I don't need to index it. I'll plot 0, 1, 2, 3, 4, 5, 6 on the x-axis, and then the cosine, and 0, 1, 2, 3, 4, 5, 6, and the sine. So let's see what that looks like. And we have the cosine is in blue and the sine is in orange. I think I can plot those with circles with lines between them by adding a third argument after the abscissa, after the ordinate. Let's see if that works. Yeah, so there we have the default colors are blue and orange, but we can change those colors if we want. We can make the second color red. Now we have blue and red. And you can see there's the cosine and there's the sine of the numbers 0, 1, 2, 3, 4, 5, 6. Because we're working with sound in this course, we're going to be doing a lot of things with cosines and sines, right? A cosine or a sine sounds like a pure tone. We'll talk about that more next week. And so for the rest of today's lecture, I'm going to be talking about cosines and sines. The blue one here is a cosine, the red one here is a sine wave. And I'm going to be finding better ways of plotting cosines and sines. In particular, so far I've just been plotting, but suppose that I want to get a title and a legend and then a y-axis and an x-axis. I can do those things by specifying set title, and then I can specify what I want in the title and what the font size should be. Set X label, and that says what I want in the X label and what the font size should be. Set Y label specifies what I want in the Y label and what the font size should be. And then here I'm creating the legend. The legend should say that it's cosine and sine, and it should specify the blue one is cosine, the orange one is sine. Right? So the s.legend creates a legend that matches whatever you've already plotted. The other thing I'm doing in this plot is I'm creating an x-axis which is more fine-grained. I don't really want to just plot 0, 1, 2, 3, 4, 5 on the x-axis. I really would like to have 100 points between 0 and pi, right? I'd like to have 0 and then pi over 100 and then 2 pi over 100 and so on. Let me actually plot those and show them. Let me plot with circles and dashes so that you can see where all of those points are. So you can see there's 100 points in this cosine, and there's 100 points in this sine. And I get that by specifying theta is the angle, and cosine gives me the cosine of that angle. Theta is the angle, and sine gives me the sine of that angle. Notice here I've used the same word cos as the name of the variable. It's also the name of the function. But those are different because the function is np.cos, and the variable is just called cos. So those are, nothing is being overwritten inside of Python. It has separate places in its variable lookup table, one for the variable and one for the function. Right, so I can use set title, set X label, set Y label, and legend in order to specify what I want, and the title, the X label, the Y label, and the legend. Those are the main things that I want to talk about today, but there's two extra kinds of plots that are really useful, and those are called scatter plots and stem plots. You've already seen a scatter plot. A scatter plot is just a set of dots where the y-axis and the x-axis are plotted separately. So I can have 20 dots between 0 and pi, including 0 and pi, and I can plot the cosine and the sine of those 20 x coordinates. So I can create this plot figure and I can create the subplots and then I can plot the cosine, and that will be cyan and it'll be symbol number 1, and yellow and symbol H, whatever H is. H is a hexagon, I think, and 1 is this downward pointing triangle, and it will show those results. Yeah, back to this one, right? Maybe I want to change those. Maybe I want that to be a red, and let's make it a, oh, what's a capital S? Will that be a square? I think that's a square. Nope, capital S is nothing at all. Let's use an O then. A red O and a yellow hexagon. There we go. There's a red O and a yellow hexagon. The nice thing about this scatter plot is that it doesn't need to be sequential data like this. In fact, I could plot the cosine as a function of the sine. Let's plot the cosine as a function of the sine with red dots. And the legend is not going to work, so I'm just going to comment out the legend line. So now I'll plot the cosine on the x-axis and the sine on the y-axis. And you'll be able to see a complete cycle. Let me actually make this, well, this should be from 0 to pi, so this should be half a circle. And so you see here's the top half of the circle. The cosine goes from 1 to -1, and the sine goes from 0 to 1 and back again. So the sine is on the y-axis. I put the sine on the y-axis, and the cosine is on the x-axis. Let me just specify that. Cosine, and the y-axis is sine. All right, so there's the sine of the angle as a function of the cosine of the angle. If I wanted to make a complete circle, then I should make dots between 0 and 2 pi, and let's make 100 points covering the complete circle. There's the complete circle going between 0 all the way around and then back again to 0 with 100 points sketching out the entire circle. Notice that it's kind of squashed. That's just because I specified that the figure should be 14 by 4. I can make it a little bit less squashed if I make the figure roughly square-shaped. 6 by 6 won't make it perfectly square-shaped, but oh yeah, there we go. There's a nice circle. Okay, so that's a scatter plot. I've created a sine and cosine as a scatter plot, and I can create a complete circle in that way. The other plot that's really useful when you're dealing with audio is something called a stem plot, which is shown here. The stem plot is a little bit different. We can't specify multiple XY pairs in order to create a stem plot. So we'll take this subplot. We'll first of all create the figure, and then create the subplot, and then we'll create a stem plot, which is the cosine as a function of theta plotted in green, and another stem plot, which is the sine as a function of theta plotted in blue. And the result, of course, looks like this. We have the cosine, which is green, and the sine, which is blue. The legend is showing them, cosine in green, sine in blue. And the stem plot is basically a scatter plot with this stem attached. So that these are sometimes called lollipop plots because it looks like the candy, right? We can go and I'm not sure if you all know the word lollipop, so let me bring up a lollipop. There's a lollipop. That's a lollipop. It's this kind of candy. So, so these are sometimes called lollipop plots because it's got a circle at the top and then a line connecting it to the x-axis. Notice this is the y equals 0, the x-axis, right? And that allows you to see each of the points. Here we have 20 points on the cosine and 20 points on the sine. So the advantage of a stem plot is that it allows you to carefully look and see exactly which points those numbers are. We could also plot them. Let's just add a real plot. So we can take s dot plot theta and the cosine and theta and the sine. I wonder if the legend will work with that. So here's the cosine is connecting it with the blue line, and the sine is connecting it with the orange line, right? So we've got the stem plot of the cosine is green, and the line connecting it is blue. The stem plot of the sine is blue, and the line connecting it is orange. And you can see that we can do the plot in order to connect them, or we can do the stem plot in order to show the connection back to the x-axis. All right, that's all the material I had to cover today. I wanted to talk about NumPy, and I wanted to talk about Matplotlib. So let's talk about how to do the homework. The homework actually has 3 different functions that are using, 2 that are using NumPy and 1 that's using Matplotlib. So let's open it up and take a look. These 3 functions are the center of gravity, the matched identity, and the sine and cosine. So center of gravity, let me show you what that looks like. The center of gravity is the imaginary point of an object on which it would balance, right? I think I have a pointer to it here. Center of gravity. No, I don't. Um, so the center of gravity looks something like this, right? It's the point at the center of it's the point at the center of the object. And you can find the center of gravity of any object by adding up how much mass there is at each of these points. And that will tell you where on that object it can be balanced. Oh, I know. The figure that I was thinking of is on Wikipedia. Let's see if I can find Wikipedia. This is the one I'm thinking of, center of mass. So here's this wonderful figure. We've got this complicated bird, and you can balance if you put your finger right at this point, not at the midpoint, which is over here, but at the center of gravity. The center of gravity is calculated by taking how much mass there is at each point and multiplying by that point. And so we create sort of a weighted average. That weighted average is calculated as shown here. We take 0 times x0 plus 1 times x1 plus 2 times x2, and so on, where each of these points is the amount of mass at one location, right? We have lots of mass here, a great deal of mass here, very little mass here, very little mass here, very little mass here. And so this is actually calculated by taking the dot product between the index vector, 0, 1, 2, etc., multiplied by the x vector that has all of the locations. All right, so we want to take n is equal to, oh, it looks like I've actually given you solutions. Well, that's convenient. We can just take n as a list of indices between 0 and the length of x. So the a range here goes from 0 up to 1 minus the length of x. And then we can take the dot product of that. And then we need to divide that by the sum of all of the mass in order to make this an average. And that should return the center of gravity. If this is already there, let's see if this already works. If I take the center of gravity of 1, 2, 3, 2, 1, that center of gravity should be 2. It's calculating as, oh, that's because this is not a 2. If I make it perfectly balanced, 1, 2, 3, 2, 1, that center of gravity should be 2.0. So the center of gravity is this item, which is item number 2. Right, I'm taking 0 times 1 plus 1 times 2 plus 2 times 3 plus 3 times 2 plus the 4 times 1. All right. This week's homework may be very easy if I've actually given you the solutions already. It looks like I may have already given you the solutions, but if so, then congratulations, you've already got the homework done. Matched identity. I want to return an identity matrix I, which is 2 dimensions, where it has the same dimension as the vector x. So if x is a 3-dimensional vector, then I want to create the identity matrix, which is 3 dimensions. And so, for example, so if I print off the instructions, there's the instructions. If I input a 5-dimensional input, then the output should be a 5-dimensional identity matrix. And it looks like that's already satisfied. And then finally, homework problem 5.3 takes a starting time and an ending time and a number of steps. And what it should return is a t vector that specifies the time axis, which should be t start through t end with t steps. So that should be the linearly spaced array between t start and t end with t steps. And the cosine array, the cosine of t, and the sine array, the sine of t. So if we plot those, we should get a plot that just shows the sine and the cosine. So this is returning homework 5 sine and cosine from 0 to pi with 20 points each, and we get the sine and cosine array. If we run the grading code, this should return 100%. So I'm not sure actually if I distributed to you a version of this homework that has all of the answers already in it. If I did, then you can go ahead and just submit that code. Let's try opening GitHub Desktop and checking it in and see what happens. And if I didn't distribute that to you, if you have a homework that's not yet completed, then please go ahead and try and complete it according to these doc strings and according to the version that I just showed you. So let's try committing this. It seems to be saying that I can't commit anything because it's exactly the same as it was. So let me just create a trivial comment here and save it just so that I have something to upload to GitHub. Now let's commit this to main. No local changes. I think I just made a change. I wonder if I'm not in the same folder. Let me go to my GitHub account and see what it shows. Here I am in JHasAgo student. And let's go to lecture 5 and see what it shows. No, that's not showing that. I wonder if I'm in a different version of the course. Let me just quit this out and see. Oh, that's it. Yeah, I have multiple copies on my hard drive of this course. So I should be actually in KCGI. All right, let's try running Jupyter Notebook again And I'm going to go to a different version of the course and show you how to do the homework in a different version of the course. I'm sorry, the problem is just that I have multiple copies, some with the solution already written and some that don't have. I want to go to KCGI, Intro Speech Understanding, and go to Lecture 5. And in this copy of Homework 5, we should find that things are not already solved. Okay, so let's create an index array, which will be the A range going from 0 to the length of x. And then let's create the dot product of the index array and x divided by the sum of x. And then we'll return C. Let me save that version. And then let me start up the Jupyter Notebook and see if I can read that in. Okay, now let me try reading that in. If I read that in, I get that, yes, the center of gravity here is 2. If I change that to a 1, I should get a slightly larger center of gravity because that's pushing the center of gravity a little to the left. If I run homework 5.2 right now, it'll just return a 0, so let me change that. I've given an array x, which has length n, so I need to find out n is the length of x. And then I want I to be just the identity matrix of size n. Let's return that. Let me reload homework 5 and run that code, and then I get, there's a 5 by 5 identity matrix. And now let's go to sine and cosine. I want t here to be linearly spaced between t start and tn with t steps. Then I want x to be the cosine of t, and I want sine y to be the sine of t. And I want to return those. So let me save this function. And then let me try running that. Here we go. Now I've got the sine and the cosine. Now if I run the grader, it gives me 100%. Okay, now let me try GitHub Desktop again. Now it's showing that I've made all those changes. So let me commit that code to main and then push it to the origin. And now let me try going back to my GitHub account and reloading this page. And now it's showing that the code is completed. And so now I can take this URL and copy it and go to the Canvas page. And go to homework 5 and simply here enter the URL of your copy of homework5.py. So enter the URL there of your copy of homework 5 and I will be able to grade it there. All right, I'm going to stop recording at this point. And